Hello, everyone. Welcome back to our webinar series. We are happy to see all of you here today. Firstly, let us check the sound and picture quality. Please tell us in the comments box if you can hear us well and see the presentation. Type something like a plus or hello in the comments box. Can you hear us? Please let us know if you can hear us. Yes. Thank you. Let me introduce myself. My name is Alina Zharikova, and I'm a business development manager of RULA Technologies. And today I will be moderating the webinar. Next to me is sitting our software engineer and Ansibas speaker, Philip Stumschatz.
Hello, everyone. Today we are going to talk about microphone calibration. And before we start, let's tell some information about RULA Technologies.
Yes, let me tell you a few words about RULA Technologies. RULA Technologies is a European manufacturer of test and measurement instruments. The company is headquartered in Riga, Latvia. We implement customized solutions for automotive, aerospace, research, and other industries. We mainly manufacture vibration controllers and data acquisition systems and softwares. By the way, we have 3 types of softwares that we manufacture: test up for vibration control, signal up for signal analysis, and calibration software for calibration. Now just a few words about technical moments. Let's have a closer look to technical side of the webinar. To ask your questions, you can use a raise your hand tool or a question section. A raise your hand tool can be also used if we have some technical problems and you just want to let us know that something goes wrong. I think everything is clear, and without further ado, I can give the floor to our today's speaker, Philip Stumschatz.
So, hello everyone again, and today we're going to talk about RULA microphone calibration module, its features, ways of usage. We will discuss calibration classification. We will make a small overview of the equipment. I will describe the software features, and we will make a microphone calibration example. So I hope this webinar will be interesting and worthwhile. Our first step is to classify the ways you can calibrate your microphone. Here you see that we can divide all the calibration methods into 2 groups. The first one uses the free field, and the second one uses sound pressure. So our first.
So as I can see on the screen, according to the scheme, I can see, for me it seems that calibration by sound pressure is a little bit more complex. Am I right, or they are the same?
These calibration methods are based on different principles. I'll describe them a bit later, and they use different equipment. For example, for free field calibration, we use an anechoic chamber, and for sound pressure calibration, we can use a coupler or a sound actuator. And now I think we can go to free field based calibration. Free field is such a field in which the sound waves travel freely without any reflections or disturbances. The main example of the free field is anechoic chamber. Here you see it on the screen. And free field is very hard to come by. However, you can make the free field in these chambers or in the open air. The main principle is based that we don't have any reflections, So we have an ability to calibrate our microphone in such chambers. After that, we go to sound pressure-based calibration. This principle is based on the idea that the amplitude and the phase of the sound wave are the same at every given point of the field. So that means we have a really small space, like in the actuator or sound acoustic calibrator. And in that case, we can think that amplitude and phase of the sound will be the same at every point of this chamber.
Is there a difference between application areas for these methods?
They are different only in features in the software. For example, we can use a regular sine wave calibration when we generate a sine signal with the desired frequency, for example, based on the third of the octave frequency row, or we can use more exotic ways. For example, we have a logarithmic sine chirp implemented here, and I'll show you it today. Also, we experiment with other different signal waveforms. For example, we're testing a linear sine chirp. Maybe in future we'll have random signal calibration, and we're testing a delta function calibration also. Maybe they won't have much precision, but it is done in case of the research.
Thank you.
So here you see the main table for the microphone calibration equipment. When we use free field calibration method, in that case we need a reference microphone, a microphone on the chair. Of course, we need our RULA vibration controller. Microphone amplifiers are optional, and we need an anechoic chamber. The main disadvantage of this method is that the anechoic chamber is really expensive and difficult to build. There are some examples of really small anechoic chambers, but their quality is not always really high. So maybe if you have such chamber in your location, you can use it, and in that case, you'll get really good results.
So can we say that calibration by free field is more complex, more complicated to arrange?
Yes, it's more complicated, but you can get really good results using this. The precision is really high. And if you have a regular lab, calibration lab, you can use actuator or coupler based on sound pressure methods. Using the actuator, you need your microphone on the chair. The reference microphone is optional, and in that case, you need to have electrostatic actuator, acoustic calibrator. It may be, in case you have a reference microphone, you don't need a reference acoustic calibrator. So you can enter the sound pressure level in the software, and in that case, you don't need reference microphone. As always, you need our controller, and amplifiers for microphones are optional, and you need an actuator amplifier. But we can use also a coupler. In that case, we don't need an actuator or calibrator. I will show you in the screen how the coupler looks like. And this is the main table for equipment. So the main way you can, and the fastest and the easiest way is to use sound pressure method with actuator. So here, let's discuss the sound pressure calibration steps using the coupler. You can see it in the screen here. On our first step, we make measurements with two microphones, the reference and the microphone under check on their base frequency. And after that, we go through the desired frequency row and generate sine waves and get the data. And after that, we calculate the FRF, find the nonlinearity, and create a report. Here you can see the main connection scheme. We have our controller, two microphones inserted in the coupler, and maybe you can have a preamplifier for your microphones. Here you see the main formula for this. The sensitivity of the microphone, which is being verified, is calculated by the division of the voltage value at the output of this verified microphone to the voltage value of the reference microphone divided to its sensitivity. It's the main formula for this. And after that, we calculate deviation according to the values on the base frequency. Also, when you use sound calibrator and actuator, it is being more complicated. On the first step, you need to place the microphone under check into the acoustic calibrator. And in that case, you find the sensitivity of the microphone on the test. Also, if you don't have a reference acoustic calibrator, you need to find the sound pressure level using the reference microphone. Here you see the formulas and the connection scheme. I think you will get this in the follow-up. After you've measured the sensitivity of the microphone under test on the base frequency, you can go to the next step. You connect your microphone under check to the actuator. Actuator connects with the amplifier, and all of this is connected with the controller. Here we start to generate our sine wave here, and after that, using this formula, we calculate the sensitivity deviation. Also here,
I'm sorry, today we're discussing a lot of formulas, so the question is that I hope that all of these calculations are made by our software, aren't they?
Yeah, all the calculations are made automatically. You get these values in the report. You don't have to calculate something manually.
Excellent.
And here, let's talk a little bit more about logarithmic sine chirp. You see this signal here, and here's the spectrum of this signal. This way, we can speed up the calibration. We use our actuator, and instead of generating single frequency, we generate the sine chirp. For example, for 8 or 10 times, get the spectrum. After that, we correct its average and get our results. The precision is really close to the values which are captured in a more traditional way, but we can save our time. So this calibration may take, for example, 5 minutes. And if you need to check or calibrate a big number of microphones, you can use it and save your time. And let's talk about the formulas for this method. Here, firstly, we need to make corrections for our microphone signal. To use it, we get the spectrum of the microphone output signal on its central frequency and correct it using the reproduced signal at the base frequency and if frequency. And after that, using this formula below, we calculate the deviation. And finally, let's talk about free field calibration. Here you see we have our controller, an anechoic chamber with a speaker inside and a microphone. On our first step, we measure voltage levels on the desired frequencies using the reference microphone. So we get, I can say, ideal values for these frequencies. And after that, we change our microphone to the microphone under check. And sorry. And we start to generate all these frequencies with the voltage values captured from the previous step. Now I think we can go to our software. Here we have microphone calibration module. It's placed under the sensor calibration. And let's go to test settings. Here our first step is called microphone parameters. Here we can enter the microphone FREF, which will be used with the coupler. Here we have options to enable anechoic chamber, coupler for the base frequencies, and the usage of the coupler. After that, we can select the reference microphone parameters, selected from the database. And here you see that if we know that our microphone calibrator is idle, we can select it to use it as reference. We have this type of calibrator, so I will enable this feature. And here we need to set the sound level in this calibrator. We will use 94 decibels, so we click this. After that, we need to select our microphone. We can select it from the database. Today we have a basic microphone with sensitivity of 50 millivolts per Pascal, and it's connected to the first channel, and its type is linear because it has output power supply with an amplifier.
Can we enter any type of microphone model?
Yes, we can add it to the database. Like here, you can press add, enter its parameters, and change its type to IP.
And how many microphone manufacturers do we have?
Here we have some, I think, all of the main manufacturers, but if you need, you can write us an email and we will add them or add them into the database, which will be sent to you. So here we have our basic microphone. After that, we go to the next step with measurement parameters. Here we have our base frequencies, 250 Hertz, and the number of averaging. I don't want this calibration to go for a long time, so let's enter 4. Here you enter the environmental parameters like temperature, pressure, and humidity. And sorry, if you want, you can enter the actuator and the amplifier FREF. Here we select no. Here we enter the frequencies for FREF only linearity calculations. Here you see set of frequencies. Here we see the main third of an octave row, but I want to make it less, so let's enter 100 Hertz and 1000 Hertz. Here you see our frequencies. Here we enter the deviation limit and the number of averaging. Our first calibration will be done with the regular sine signal, so we don't enable sine chip for actuator. And now I think we can start. Let's press start button. Here you see that we need to connect the microphone, which is being checked to the calibrator. And I will enable it right now. And let's turn on the camera. Here you see our microphone, actuator, and sound calibrator. And let's press OK. And sorry, we need to make it again because I forgot to enable the power supply for the microphone. Let's redone. It will be redone. And here you see the sine signal, the input values, and the input in decibels for our calibrator. We need to wait some time. After that, we go to F-rep nonlinearity step. And here I need to place my microphone into the actuator. After that, I will turn on the amplifier for the actuator. And now let's press start. You see the switching frequency, and I'll stop talking because it influences my. So here you see that the report is being created automatically. Here you see the resulting sensitivity, the FRF unlinearity in decibels and in percent. Here you see the table with all the measurements. And let's wait some time to get the full report. Here is created. Let's close it. Here you see that report creation is complete. And after that, you see that our FRF nonlinearity is okay. And after that, we can remeasure all the steps, make manual calibrations. And for all these features, you can increase your results by entering the higher number of averaging. Also, we have an option which remeasures all the values each time we, for example, influence our microphone with sudden noise. For example, someone entered the room and closed the door, and in that case, we will remeasure all measurements done for this particular frequency when it was done, because we influence the microphone with the sudden noise. So we have this type of measurement protection. Also,
and how long does this test run usually take?
for example, if we want to calibrate our microphone from 0.1 Hertz up to 2000 Hertz, 20,000 Hertz, with averaging number of 8, it may take, for example, 30 or 40 minutes. Now we will use our sine chirp. Here you see an option. I'll enter its duration to 6. After that, we need to have an output signal monitoring channel. It will be the third channel. And here we need to control our output voltage not to damage our microphone. In that case, I put a BNC T-type connected to the output, connected with an actuator amplifier, and with our controller with its third channel. As I mentioned, here we have logarithmic sine chirp, linear one, and the delta function. We use logarithmic. Here we see our output channel, and after that, let's press apply. And to do this, we need to remeasure first step with the calibrator. In that case, I need to disable my amplifier. And I need to reset the microphone. So let's start. Here we remeasure.
Please tell us if you can see the video.
I think we can reset the camera. I think it's working now. If you have some camera issues, please write in the questions. So now we go to the next step. And here I need to place my microphone again into the actuator. So the setup is done, we can continue. And we press start. And here you'll see we will measure the base frequency, and after that we will generate a sine curve. Here you see it. I can say that if you sit near the microphone, you'll be able to hear this signal. So here we'll have a report again. And as I mentioned, it takes less time. And here you see that our resulting sensitivity is really close to our 50 millivolts per Pascal, and our FRF nonlinearity percent is lower than in the previous variant. Here you see all the calculated values.
While we are waiting for the reports being built, Philips, can you please tell us if we need to enter the reference data of microphone under check every time, or it will be automated entered?
So if we have our first calibration weight with the microphone calibrator, and we don't have a reference calibrator, we use our reference microphone only once to measure the sound pressure in the calibrator. In case we calibrate our microphones using free field and an aquator chamber, we perform these measurements and we save all the measured data for the selected reference microphone. So you can measure it once, and after that, if you don't change it, use these measured values as reference and speed up the calibration process. So here we can close the report. And now I'll show you some more settings here. In case of coupler, you need to enable it. And as I mentioned, here we have the delete temporary files at the end. If we check it, we won't delete any measurements and we will save them. So you can continue or remake your measurements. After that, here we can rewrite TEDS data. If we have a TEDS microphone, use field corrections. And if we have a coupler, we can save our time because the first and the second step are done without any equipment changes, and we will automatically go to the second step. I think that's all about the settings. Let's go back to presentation. And so today I told you some information about the microphone calibration module, told you that all the calibration ways is based on two principles, sound pressure and free field. We discussed all three ways to calibrate the measuring microphone and discussed the advantages of each method.
Now I would like to ask several questions to Felix, and maybe while I will be asking them, you will also have a desire to ask something about microphone calibration. So the first question is, what standards do we follow?
Using the microphone calibration, we follow IEC 61094. It's the basic microphone calibration and verification standard.
Mm-hmm. Okay, I see. As far as I know, a few years ago, there wasn't an option of microphone calibration by free field, and now we have it. What's your opinion? Is it a must in test tab for microphone calibration, or it's just a great addition? And answering this question, can you say us which method is more in demand, by free field or by pressure?
So the free field, as I know, is widely used when some manufacturers create, for example, some smart speakers. For example, as I know, Apple calibrates their microphones in anechoic chambers, and in that case, we have this ability to do this in anechoic chamber to calibrate the microphone. But if you have regular microphones, you don't have some specific measurements, you don't need to get too high precision results. For example, you need to measure, for example, the throttling of an engine or something like that. In that case, you need to calibrate your microphone, but you can use a regular actuator calibration. You don't need this precision quality as in an anechoic chamber. And of course, these chambers are really expensive, and so it's hard to find them, as I know.
Thank you for an extended answer.
So if you have any questions, please write us and we will answer, or you can write us an email and maybe I can answer it with more detailed explanation.
Oh, I can see one question. So thank you for the question firstly. And it is, do we have diffraction correction option?
Yes, I think we have another name for it. It is used in anechoic calibration here, and we called it, according to the method, free field correction. It's here.
Is there an opportunity for customization of the report?
This is a good question. Now we created a report tool using file templates. We have ODT templates in your RULA folder with desktop. Here you can see it. Here you see a report template. In this template, we have names for the values. You can enter your company logo or even create your own template based on fields which we have in this template. And this way you can create your custom template, and maybe in future we will have a report template creation wizard, and many customers ask about this, and now you can do it manually using these ODT templates.
Great. So I would like to thank all of you here today for being with us. I hope that this webinar was interactive and worthwhile for you. It was the last webinar in season 2023-2024, and we will see you in the next season in autumn.
So thank you for watching. Have a great day.